So we study how to some operation in binary system, how to add, how to minus, right? Right. Okay. Okay, so we continue to study the sorry. Okay, so last week we studied how to do some operations in binary system, like how to add and how to subtract, right? Okay, so we continue to talk about the octal system, the octal numeral system. So in the octal numeral system, the base b equal to 8. So we use 8 digits consists of 1, 0, 2, 3, 4, 5, 6, 7. So total 8 digits to build an octal numeral system. So in this system, when we use n digits, we can represent h power n different values ranging from 0 until 8 power n minus 1 value. So example, when we use 2 digits, so we can represent h power 2 that equal to 64 different values. So start from 0, so 1 until 63. Okay, that is so someone have any question or any comment? Okay, so in the octal system, given that a number a, which is represented using octal system, so we denote as a equal to an. So n is suffix an minus 1 until a0. That is the integer part of the number, and dots and fraction part. So for the fraction part, we index from minus 1 until minus m. So this is the general way to represent a number. It consists of two parts, integer part and fraction part, separate by a dot in between. And we know that when we index for the integer part, we index from 0 and from right to the left. And for the fraction part, we index from minus 1 to minus m and from left to the right. Okay, so given this number A, we can determine the values of A using this formula. So the values of A equal to AI multiple with BI, in which I is the index and I running from minus M until N. And here B is the base of the system. And in the octal system, B equal to H. In the binary system, B equal to 2. And in the hexadecimal system, B equal to 16. So this formula is the general formula to determine the values of a number in any B-based system in the decimal system. Okay. Example, given number in the octal system, example number that is 235.64. So the subindex H here, it means this number is in the octal system. So we can determine the values of this one in the decimal system by applying this formula. First of all, we index the digits. So the index of 5 here is 0, index of 3 here is 1, and index of 2 here is 2. So we have the formula 2 multiple with h power 2 because the base equal to h, right? Multiple with 2, 3. Multiple with h power n because the index of 3 is 1 and index of 5 is 0. So here 5 multiple with h power 0. That is for the integer part. For the fraction part, we have here the index of 6 is minus 1, and here 6 multiple with 8 power minus 1, and 4 index minus 2. So 4 multiple with 8 power minus 2. So finally, you have this number 235.64 in the octal system. The value in the decimal system is 157.h125. So this is the values of the octal number in the decimal system. And this is the way to convert a number from the octal system in the decimal system. And note that this formula is the same for converting from a different B-based system into the decimal system. Okay. This table shows the respective values of different number in the binary, in the decimal, in the hexadecimal system. Okay, so example number, the first column is number is a decimal system. Okay, the second column is the number respectively in the binary system, and the last column is number in the hexadecimal system. Okay, example number 9. Number 9 here in the decimal system, so it's binary, it will be 1001, and also it is 9 in the hexadecimal system. Or another example is number D. Number D in the hexadecimal system, in the decimal system it will be 13, and in the binary system it will be 1101. So I think you should remember this table so that you can easily or quickly translate the value from this system into the other system. Okay. This is the same formula as in the octal system, but we replace the base equal to 16. So given that a number in the hexadecimal system, you can use this formula to convert it into the decimal system with the base b equal to 16. Use the same formula. Okay, example, given a number in the hexadecimal system equal to 34F5C.12D. Okay, so to determine its value in the decimal system, first of all, we need to index the digits. So the index of C equal to 0 and C equal to 12, right? So we have 12 multiple with 16 power 0. Okay, number 5 here, index 1. So here we have a 5 multiple with 16 power 1. And also example here, F index is 2 and F equal to 15 is a hexadecimal system. So here we have 15 multiple with 16 power 2 and so on. And here, example, the digit D, the index is -3, right? -3. And D equal to 13, right? D equal to 13. So here we have 13 multiple with 16 power -3. It means 13 divided by 16, 16, 16. So in this way, you can determine the value of this number in the decimal system. Okay. We talk about the decimal system. We also talk about the binary and the octal and the hexadecimal system. But in general, we have a B-based system, and we can convert the value from B-based system into the other system. And we also can convert a number from this system into the B-based system. Okay, so in general, a number n in the decimal system, so we denote by n subindex 10. It means this number n in the decimal system should consist of two parts. One is the integer part, and the other one is fraction part. They are different. They are separated by a dot sign, right? To convert the number from other system to the decimal system, we use the formula that we talked in last slide. And now to convert a number from decimal system into the other system, like the binary, the octal, or the hexadecimal system. So we will using two steps. The first one, we convert the integer part of the decimal system to the B-based system, and then we convert the fraction part from decimal system into the B-based system. Okay. For the integer part, we will use this algorithm. We divide the integer part of the number in the decimal system by the b, in which b is the base of the system that we want to convert to, right? So we obtain the result that consists of T1, which the remainder is D1. If T1 equal to 0, so we stop. If T1 is different from 0, we continue to divide T1 by B, and again we obtain the result that is T2, with the remainder D2. Okay, and we continue until the result Tn equal to 0 and stop. And the results of the number in the B-based system will have forms of D1, Dn minus 1 until D1 in the B-based system. It means we convert the number n in the decimal system into the number Dn minus 1 until D1 in the B-based system. Okay, this is the algorithm to convert a number from the decimal system into the B-based system. Okay, so here is an example. We convert the number 12. We convert number 12 in the decimal system into the binary system because the base of the binary system is 2. So we divide 12 for 2. We obtain the result equal to 6, and the remainder is 0, right? Because 6 is different from 0, so we continue divide 6 by 2. We obtain 3, and the remainder is 0. 3 is different from 0, right? So we continue to divide 3 by 2. We obtain the result is 1, and the remainder is 1 here. Again, 1 is different from 0. We continue to divide 1 for 2. We obtain result is 0, and the remainder is 1. Okay, so when we convert the number 12 in the decimal system into the binary system, the result is 1 1 0 0 1 1 0 0. So it means the number 12 in the decimal system equal to the number 1 1 0 0 in the binary system. Okay. Now, okay, can you do an example? Given the number 21 in the decimal system, can you convert it into the binary system and give the answer to the meeting chat? Okay. A small exercise. Given a number 21 in the decimal system, can you convert it into the binary system and write the answer to the meeting chat? Okay, so Văn Ngọc and Mạnh Hùng gives the answer. Okay, 21 divided by 2 equal to 10, right? And remainder 1. Okay, so I think it's simple. So most of you can give the answer, and hopefully it's correct. Okay. That is the way to convert the integer part. For the fraction part, okay, for the fraction part, we use the different ways. For the fraction part, we multiple the fraction part into the decimal system with the b, the base of the system, right? We multiple with b, so we obtain a result in forms of x1, y1, in which x1 is the integer part and y1 is fraction part. So if y1 is equal to 0, so we stop. If y1 is different from 0, we continue to multiple 0.y1 with b, and again we obtain the result in forms of x2.y2. So we continue until the fraction part of the result yn equal to 0, so we stop. Okay, and the result will be in the forms of 0.x1, x2, xn, in which x is the integer part of the step n. Okay, this is the result to convert a fraction part in the decimal system into the B-based system. Okay, so here is an example. We need to convert the number 0.6875 in the decimal system into the binary system. So the base equal to 2. So we multiple this number with 2. We obtain the result is 1.375, in which 1 is the integer part and 0.375 is fraction part. Because this fraction part is different from 0, so we continue to multiply 0.375 with 2. We obtain the result 0.75. We continue multiple 0.75 with 2, we obtain the result 1.5. And again, we multiply 1.5 by 2, we obtain the result 1.0. At this step, the fraction part of the result is 0, so we stop. And the result is 0.1011. So it means the number 0.6875 in the decimal system equal to the number 0.1011 in the binary system. So this is the way to convert a number in the fraction number in the decimal system into the binary system. Okay, so it's simple. There are some small exercise for you. So here's 4 exercise. The first one and the second one, convert a number from decimal into the binary system. The third one, convert a number from binary into the hexadecimal system. Last one, convert a number in a hexa to the binary and from hexa to decimal system. So can you do it and give the answer to the meeting chat?
Can you show the last example real quick?
Sorry?
I want to see the last example at converting the fraction.
This one you mean?
Okay.
Okay.
I mean the example, the last example of the fraction part.
Yeah.
Can you show it again? Real
This
quick.
one, okay.
I don't see the screen changing.
You don't see? Okay.
I mean the example where you show how you do it.
This is one.
Yeah, please. Thank you.
Okay.
Done. I'm done.
So I move to the exercise.
Yes.
So Đỗ Huy Vũ gives the answer for the exercise 1. I think it's correct. I think so. Okay, so how about the other one? So I think there are at least some questions about this exercise in the midterm and also in the final exam. So I think you should learn how to do it, even it's so simple. But if you don't do or don't practice with exercise, it takes time to calculation, because there are at least some question about this exercise in the midterm and also final exam. So I think you should find the result within a minute for each question, because in the exam there are lots of questions. So I think you don't have time for you to learn the formula during examination, right? Okay. Okay, so we move to the next. So we study about the numeral system. So in computer science, there are 4 popular systems. That is decimal system, binary system, octal system, and hexadecimal system. Actually, we use decimal system because it is popular, so it is used every days in your life. We study binary system with only 0 and 1. This system computer can understand directly because it respect with 2 status of the electronic component, like on or off, yes or no, right? So 0 and 1 in the binary system is similar to 2 status like on or off, yes or no, in the electric or electronic or automatic system. Okay, so with binary system, computer can understand directly. And you also study about the octal and hexadecimal system, because this is the way to represent the binary system shortly. Because example, when we want to represent a number like 1,000 or 1,000,000, we need a lot digits in the binary system. But when we use the hexadecimal system or we use octal system, the number of digits is much smaller, because 3 number in the binary system equal to 1 digits in the octal system, and 4 digits in the binary system equal to 1 digit in the hexadecimal system. It means you can decrease the number of digits 3 times or 4 times in the octans or hexadecimal system respectively. Okay, so in the next part we will talk how to represent data in computer. So example, when you make a picture about yourself or about some flower, okay, some thing outside. So when you use your smartphone, you make some picture, right? And then the picture is stored in your smartphone, and then you can share the picture or send it to the other one. So how can the picture? So the picture will have your face, your body, or some flower with different color, different brightness, different solution, different contrast, right? But how can it start in your smartphone? Because in your smartphone, it also a computer, right? In a computer, only number 0 and 1 is stored in the memory, only two stated 0 and 1. And how to use this number 0 and 1 to represent the picture with color, resolution, and something. Okay, so that is the way we learn how to represent data in computer. So all data, all things that store in computer must be encoded into the binary number. So example, you send a text to your friend. Example, we send good morning. Okay, sorry, good afternoon. You send a text good afternoon to your friend, right? So good afternoon, you have the first character is Z, right? The second and the third is O, right? And then D, okay, and then A, and then F, and then T, E, R. So that is the character in the string good afternoon, right? So each character is encoded by a number of binary digits, and because the number in binary digit is only 0 and 1, it means when you type good afternoon, it means a series of binary digit is input to the computer or to your smartphone, and then that series of binary digit is stored or is sent to your friend. So this is the way we store or we process or we retrieve or we send whatever data in the computer or through the network. Okay, so data in computer is classified into two types. The first one is basic data, such as the character ABC or the number, the integer, the real number, that is basic data. The second one is structured data, so like a picture, right? So how can represent a picture? How can store a picture in your computer? So example, you make a picture which the resolution is, example, very small one, like 1 megabyte picture. So it means the picture has, actually the picture is a matrix of different point, right? Example, the matrix has 1024 line and 1024 column. So it means your picture has the resolution is 1 megabyte on 1 mega point. So each point will be which point consists of different information like the color, the contrast, and something. So each kinds of information is a real number or a integer, and we also represent that a real number or a integer into the binary number, and then we store all the binary number of the picture in computer or smartphone. So this is the way we store a structured data like a picture in computer or in smartphone. Okay, so for the basic data, we have integer, we have a real number, and you have character, 3 kinds of basic data. Okay, so we will study how to represent these kinds of basic data in computer. So for the integer, we have unsigned and we have a signed integer. For the unsigned, so it is simple. We can represent by convert it into the binary number, as we study in the first part of the lesson. Okay. For the signed integer, we using the second complement encoding. It means we use some kinds of binary to represent the unsigned, and then we use some kinds of binary digit to represent the size of the integer. For the real number, we use the floating point standard we study later. And finally, we use ASCII and or Unicode standard to represent character in computer. Okay, so for the structure, so we talked already. We can actually structure data, that is the complex or the combination of different basic data, right? Example, we want to represent or we want to store a picture in a computer or in a smartphone. We can structure the picture by different point. So each point there are different information. So each information may be an integer or maybe a real number. So it means when we want to store or want to represent a picture, we store a group of different real and integer number. So that is the way we store and we represent a structured data. Okay, so this slide shows the units of information. The smallest one is bit. Bit stand for binary digit. Okay. So bit is the smallest units of information, and bits may be 0 and 1. Okay. 2 digits of binary system. However, using bit, we can only represent 2 status, that is yes or no, on or off. And in real life, I think most of things there are more than a status, right? So normally we use by, that consists of 8 bits to represent. So by equal to 8 bits, and then we have a bigger one, kilobyte, that equal to 2 power 10 byte and equal to 1024 bytes. And then megabyte equal to 2 power 10 kilobyte. Gigabyte equal to 2 power 10 megabyte. And next one equal to this one multiple with 2 power 10. So we have the order kilo, mega, giga, tera, peta, and esa. And okay, so kilo is power 10, mega power 20. It's a little bit equal to million, right? Giga similar to billion. Tera similar to, not exact equal, but similar to thousands of billion. Peta similar to millions of billion, and exa equal to billions of billion. bike. So I think you need to remember this information unit. There are some multi-choice question in the midterm and also in the final examination about the information unit. At least 1 or 2 questions. Okay. In the last part of the lesson, we study 3 specific case of how to represent integer, real number, and characters in computer. The first one, representation of integer. So to represent an integer, we use a set of bits. So different number of bits for one integer. For the size integer, so it means we have a positive or negative integer. So we use the first bit to represent the size. So if this bit equal to 0, it means it is a positive number. And if the first bit is 1, it means it is the negative number. Okay, so we call the first bit is the size bit of the size integer. Okay, so the same as how to convert a number from decimal system into the binary system. So there are 2 ways. The first one, given a number in the decimal system, we can represent it by convert this number from decimal system into the binary system, right? We have a formula already. So given a number in the real life, right? It means in a decimal system, we can find how to represent it by convert it into the binary system, right? Okay, the second way, given a representation of a value in computer, it means we give a list of a binary system and how to determine its value. So we will convert this number from binary system into the decimal system. So we will have the values of that representation. Okay, so for the unsigned integer, it's very simple. Given a number in the decimal system, we can find the representation by converting it into the binary system. The other way, given the representation of a number, you can find values by convert from binary into the decimal system. We study how to convert 2 ways already, right? Okay, so we know already this one. We know already, right? For the size integer, because we have 1 bit for the size, so it is a little bit difficult to represent or to determine the value. So example, given the representation of a size integer a and the form of a subindex and -1, a and -2 until a0. This is the representation of a. It means this is binary system, binary number that represent the number a. Because a is the size integer, right? So the first bit, it means the bit a subindex and -1 is the size bit. It is used to represent the size of the integer. So if a n -1 is 1, so this is negative number. So if it is 0, it will be the positive number. So given the representation or given a series of binary digits, we can determine the values of A using this formula. So the first bit we put the sign minus here. So A, big A, equal to minus of small a subindex n minus 1 nhân multiple with 2 power n minus 1, and the rest we use the same formula equal to the sums of ai multiple with 2 power I running from 0 until n minus 1. Actually, you use the same formula except the first bit we put the sign minus here because it is the sign bit. Okay, so if we use n bits to represent unsigned integer, we can represent 2 power n minus 1 value from 0 until 2 minus power n minus 1, right? But if we use n bits to represent the sign integer, because we did 1 bit for the sign, so the values will range from minus 2 power n minus 1 for the negative until 2 power n minus 1 and minus 1 for the positive. The same 2 power n different value, but a half for the negative and a half for the positive. Okay. Okay, so I talked already. Already here. Okay, example. Given two example of A and B, which is the representation of the number in the computer, number with sign. So you can easily know that A is the positive and B is the negative number. Okay, so to find the values of A and B, we need to index the digit from right to the left. Okay, for A. So index here 0, index here 1, index here 2, index here 4, index here 6. The first bit is 0, it means it is positive. Okay, so here A equal to 2 power 6, 2 power 4, 2 power 2, 2 power 1, right? And equal to plus 86. This is positive number. And about B, okay, again we need to index this one, index 1, this one index 4, this one index 6, and this one index 7, but the first one must be the minus. Okay, so we have B equal to minus 2 power 7 plus 2 power 6 plus 2 power 4 plus 2 power 1 and plus minus 128 plus 64 plus 16 plus 2, and this equal to minus 46. So this one is representation of the sign number minus 46. Okay, so this is the way to find the values of a representation of the sign integer. And the question is, given a sign integer, and how can we find the representation? Okay, given a sign number, maybe positive, maybe negative. So how can we represent it in computer, right? The answer that is we use the second complement encoding, and this slide shows how to find the second complement encoding. Given an unsigned integer A, so A is unsigned integer. It means A is positive, right? We can easily represent A in computer by convert A from decimal into the binary system. Okay, you can easily, right? And then the first complement encoding of A will equal to the biggest number. It means 2 power n minus 1 and minus A. So if you represent A by n bits, so the first component for the first complement encoding of A will be the not of A. Okay, so example A here equal to 6, right? Here is A equal to 6. So if we use 4 bits to represent A, the result is 0, 1, 1, 0, because A equal to 6. And the first complement encoding of A will be not A. It means the first complement encoding of A will be 1, 0, 0, 1. Okay, 1, 0, 0, 1 is the first complement encoding of the number 6. And then we can find the second complement encoding of A that equal to the first complement encoding plus 1. Here you can see plus 1, right? So we, the first encoding is 1, 0, 0, 1, and the second encoding we plus 1 here, so equal to 1, 0, 1, 0. So it means given A equal to 6, and the represent of A equal to 0, 1, 1, 0, that is the representation of A. And we find the first encoding of A, that is the not of A, it means equal to 1, 0, 0, 1. And then you can find the second encoding that is equal to the first plus 1 and equal to 0, 1, 0, 1, 0. This is the second encoding of A. And then this one, the second encoding that is the representation of the number minus A. Minus A. It means 1, 0, 1, 0 is the representation of the number minus 6. So, in summary, the algorithm to find the representation of a signed number in integer, so the signed number in a computer, first we convert that number without the sign into the binary system, and then we find the first complement encoding by use the not function, right? And then we plus 1 to find the second complement encoding, and then that will the representation of the number minus A. So that is the algorithm. Okay, so here is an example. Given number A equal to minus 70, and how to find the representation of minus 70 using 8 bits. Okay, so first step, we translate the number 70 into the binary system. So we obtain the result 70 equal to 0, 1, 0, 0, 0, 1, 1, 0. So the 70, right? And then we find the first complement of 70 by using the not function. So we have the result, the first encoding 1, 0, 1, 1, 1, 0, 0, 1. Okay, 1, 0, 1, 1, 1, 0, 0, 1. That is the first encoding. And we find the second encoding by plus 1 with the first one. So we plus 1 here. So 1 plus 1 equal to 0. And remember 1, right? Here. And 0, 1, 1 here. The same. So the second complement encodings of 70 is 1011, 1010. And also this is the representation of the number minus 70. So you can check, you can test it. If this number is equal to minus 70, you can find this number by index from right to the left, right, right? So this number 1 index 1, this number 1 index 3, this one index 4, this one index 5, this one index 7, right? And the result is minus 2 power 7 plus 2 power 5 plus 2 power 6 plus 2 power 3 and plus 2 power 1, and it will equal to minus 70. Okay, so this is the way to find representation of a sign number using the second complement encoding. So is it simple? Bạn Tống Duy Kiên, is it simple?
Not very simple.
Okay. So okay, so now we'll study how to do some operation on the integer with sign or unsigned. For plus or minus unsigned integer is simple because we study last week. We plus or minus bit by bit from right to the left or right. Okay. However, here we last week we talked about how to add or minus a number in the binary system. Okay, but here we talk about the operation in the computer. So in the computer, the number of bits is fixed in advance. So, for example, we last week we study how to add two binary number. So example 1 plus 1 so equal to 0. We remember 1 and we write to the left. It means if we plus two number, so we can example 8 bits, the result maybe also 8 bits and maybe also 9 bits, right? If the last one we still remember, so the number of bits you will increase. But in the computer, the number of bits is fixed in advance. So if the last one we still remember, it means the results will wrong because that bit will be lost because the number of bit is fixed. Example, we plus two number with 8 bits, it means the results must also 8 bits. And if the last one is still remember, it means this bit will be lost and the result is wrong. So we call it that is override result. So that is the notation of how to plus and minus. Okay, here is some example. Example 1, given x and y, which is 8-bit integer. So we plus x and y is the same way as last week. Okay, 0 plus 1 equal to 1, 1 plus 1 equal to 0, and remember 1. Remember 1 plus 1 here equal to 0 and also remember 1 here. Okay, 1 plus 1, remember 1 here. Okay, so 1 plus 0 equal to 1, right? So in this operation, the last step, we don't have any remember bit. So the result s equal to 1 0 1 0 1 0 0 1, it equal to 169 in the decimal system. It means the result is correct because the last step there are no remember. It means carry out equal to 0, and the result is correct. The second example, we plus x with y. Okay, here 1 plus 0 equal to 1. 1. Okay, 1 plus 1 equal to 0. Remember 1 here. 1 plus 1 equal to 0. And remember 1. And remember 1 plus 1 here equal to 0. And we still remember 1. So the last remember here, we assign to the bit carry out that equal to 1. But because in computer, x and y is the 8-bit number, and of course s is also the 8-bit number, and bit means the last remember bit is carry out equal to 1, and then the result is not correct, it's wrong. Actually, we can easily find s here equal to, so s here, because the first bit of that is 0, so this is a positive number, and s equal to, okay, 11, 11, right? Because this number 1 index 0, this number 1 index 2, and this number 1 index 3. So s equal to 8 plus 2 plus 1 equal to 11. This is wrong because x equal to 197, y equal to 70. And the sums of x and y must be 267. But when we plus it in computer, the result is 11. So it is wrong. So we need to remember that when we add or the same, we minus 2 unsigned integer, the results may be wrong if the carry out bit is 1, or if at the last step we still have the remember bit. Okay, that is the sum. About the minus, example a minus b, you can replace by a plus the negative of b. So for the minus, we can convert the b from the b operand into the minus b, and then we do the same as a summation. Okay, so again, a minus b equal to a plus minus of b, and equal to a plus the second. We use the second complement encoding of b to represent minus b. Okay. So that is the plus and minus, the size integer. So there are some summary, some notification. Sum of two sides integers with opposite sign, the result will always correct if the size of two operands is opposite. Sum of two sides with the same sign, sum of two integers with the same sign. So if the size of sum is the same as the size of two operands, so the result is correct. So if the size of sum is different, example, we plus, because we plus two integers with the same sign, so if the size of operand is positive and the sum is also positive, the result is correct. But the sum is negative, of course the result is incorrect, right? Actually, you have overflow. It means carry out is different from 0 because the values of sum may be out of the range that we can represent using that number of bit. It means the values of the result is out of the range of representation. That's why the result is incorrect. Okay, some example of the result is correct or not. Okay, so the first one here, so x is positive, y is positive, and the sum s is positive, so this is correct. The second one here, x is positive, y is negative, so the result is always correct because we plot two different sides or opposite sides integer, so the result will always correct. The third example here, x is negative, y is positive, and of course the result is always correct. The last one, x is negative, y is also negative. It means the same sign, but the result s is also negative, the same sign as appearance, so the result is correct even the carryout is equal to 1, but the result is still correct. So these are the example for the result is always correct. Overflow. This example, x is positive, y is also positive, but the summation s is negative, so the result is wrong. And the same, the last one, x and y is negative, and the result sum s is positive, and the result is wrong. Okay. About how to multiple or division, actually we do as the same as in the decimal system. So example, we multiple two number that represent unsigned integer. So we multiple 1011 with 1101. So we multiple digit by digit from right to the left. The first one we multiple this number 1 with 1011. We obtain 1011. The second we multiple the number 0 here. Of course, we have 0, 0, 0. Next, we multiple with number 1 here. Again, we have 1, 0, 1, 1. And last one, number 1 here, we have 1, 0, 1, 1. And then we plot these four binary number. So 1, we have 1 here. 1 plus 0 equal to 1 here. 0 plus 0 plus 1 equal to 1 here. Okay. 1 plus 0 plus 1 equal to 0, right? Remember 1. And plus 1 equal to 1 here, right? So we remember 1 plus 1 equal to 0 is still remember 1. And remember 1 plus 1 here equal to 0, still remember 1. And remember 1 plus 1 here equal to 0, and we remember 1. And finally, when we multiple 1011 with 1101, the result is 1000 1111. That is the result. So actually, multiple and division, the binary we do as the same as in decimal system. Okay, the same. Division different, a little bit difficult, but actually it's the same way as in the decimal system. Okay. So example here, we divide this one. I think this example has some typo. Okay, so we divide this one 100100011 by 1011. Okay, first we take, because the this one has 4 digits. First of all, we take 4 digits, but this is smaller than this one, so we need to take 5 digits. Okay, so because 5 digits, of course, it's bigger, so the result is a 1, right? 1. So 1 we multiply this 1, we obtain this. So some table it should be 1011, and we take this one minus for this one, and this is the result, right? And we do again. Actually, the algorithm the same as in the decimal system. The same you can do. So I think we will have some breaks about 10 minutes, right? So we will come back at around 2 and 20. We will come back around 2 and 20.
Nó có quần đi hết rồi, cầm lông nha nhông không tí
Okay, so we come back to the lesson. So can you hear me, Trần Ngọc Danh? Can you hear me? Trần Ngọc Danh, can you hear me? Trương Tuấn Huy, can you hear me?
Yes, yes.
Okay, so we continue. So this table shows some operation on a bit, the logic operation. So we have and or and so, and also we have a not operation. Okay, so these operations operates on two binary number, or we can use to do operation on the integer, but it is represented in the computer. It means we can use the function and or so in the two series of binary digits. Okay, so for the n function, so the ends of 0 and 0 equal to 0, ends of 0 and 1 equal to 0, ends of 1 and 0 equal to 0, and only ends of 1 and 1 is equal to 1. For the OR function is different, so ends of 0 and 0 so equal to 0, and ends of 0 and 1 equal to 1, 1 and 0 equal to 1, and also 1 and 1 equal to 0. So it means in the n function, it both of bit equal to 1 and it result is 1. The other way, the result equal to 0. For the OR function, only 1 in 2 bits equal to 1. So the result is 1. So the result equal to 0 is only if both input bit is 0. That is N and OR function. So I think most of you studied the electronic or automatic, right? So there are some N and OR component in your logic circuit. So the principle is the same. So if both input has a signal or the value is 1, so the output is 1 if that is the N component. So only if both input is 0 or no value, so the output is 0 if that is the OR function. Also there are SAW function or SAW component in the logic circuit in your measure. I think for the SAW function, the result is 1 if the inside bit is different. Example, if the inside bit input bit is 0, 1 or 1, 0, it means different, right? So the result of SAW is 1. So SAW, the first character X, it means the difference. So if the input is different, the result is 1. So if the input is the same, the result is 0. So example, the input is 0 and 0 or 1 and 1. So the result of SAW is 0. Okay. For the NOT function, so it is the opposite of the input. Input 0, output 1. Input 1, output 0. Okay. So for the logic operation, for the serial bits, we do bits by bits from right to the left or from the left to the right, the same. Okay. For the series of binary, you can also use AND or SAW or NOT function, but we do bit by bit from right or from left. Okay. Example, we have two binary number here input in the left. So the n function we do bit by bit, the or function, sort function we do bit by bit, and also the not function we do bit by bit. Okay. Okay, next we study how to represent the real number. So in summary about how to represent the integer number. So for the integer number, we have two kinds. One that is unsigned. It means only positive value. We can represent in computer by convert it from decimal system into the binary system. Very simple, right? For the signed integer number, it means it may be positive or negative. We use the first bit to represent the size of the number. So if the first bit is 1, it is the negative, and the first bit is 0, it is positive. And to find the representation, we use the second complement encoding to represent the negative number. Okay. For the real number, it means we have integer part and we have also fraction part, right? So how can we represent in computer? We use a floating point number. So what is a floating point number? A floating point number has the form of m multiple by r power e. So this is the floating point number of the number x. So we write x equal to m multiple with r power e, in which m is mantissa. Okay, so in Vietnamese we say m is phần định trị. R is the base. Okay, so in Vietnamese cơ số, right? E is exponent. So in Vietnamese it is phần mũ. So for a floating point number, there are three information, three number that is used to represent, that is mantissa, radix, and exponent. Okay, so given a number, given a real number, we can find the representation in the floating point forms by finding the mantissa, finding the base, and also finding the exponent. Okay, and we know that even x is a real number. It means it maybe has integer part and fraction part, right? But all the values mantissa m, radix or base r, and exponent e are the integer number. So it means you can use integer number to represent a real number, but we need three integers to represent one real number. Okay. Okay, example, using the radix or base equal to 10, it means the decimal system, and given two floating point number with mantissa equal to minus 15 and plus 314, and also exponent plus 12 and minus 2. So the values of n1 equal to minus 15 multiple with 10 power 12, right? And the number n2 equal with 314 multiple with 10 power minus 2. So actually n2 equal is the p number in mathematics. Okay, there are some operations on floating point number we study in high school already, right? So example, given n1 equal to m1 multiple with r power e1, and n2 multiple with n2 equal to m2 multiple with r power e2. So we can add or subtract floating point number. So n1 plus or minus n2 equal to this one, and also multiple and divide. This formula is, I think you study already in high school. Is it correct?
No.
So which one is wrong? Which one is wrong?
Yep, I think it is not divided.
Yeah.
In the final.
Yeah. Okay. Actually, the last one is wrong. The last one is wrong. Actually, this is multiple with, right? This is multiple with power e1 minus e2. This is not divided. That's multiple. Okay. Actually, I know already, but I want to check if you are sleepy or not. Okay. Thank you. So we know that the last one here still multiple with power e1 minus e2. Okay. Okay, next we study about the IEEE 754 85 format. So shortly we say this is IEEE standard. So we know that IEEE is an international institute of standard for electronic, energy and information technology. So this is the international standard institute about energy, electronic and information technology. So this institute, this organization, they propose a lot of standard for energy, electronic and information technology, and also the standard 75485 is a standard for representation floating point in computer. So in this format, we use the radix equal to 2. It means we use the binary number, right? And there are 3 kinds of standard. The first one, we use 32 bits to represent a real number. So we say a single precision. So in Vietnamese, it is độ chính xác đơn. The second standard, they use 64 bits to represent a real number. So in Vietnamese, so it is double precision. So in Vietnamese, we say độ chính xác kép. The last one, they use 80 bits to represent a real number. It is extended double precision, and in Vietnamese, we say độ chính xác kép mở rộng. Okay, so there are 3 kinds of how to represent a real number using IEEE standard: single precision with 32 bits, double precision with 64 bits, and extended double precision with 80 bits. Okay, and here is the format of encoding. For the single precision, we use 32 bits, right? And we index from 0 until 31. And the first bit, the bit number 31, denoted by S, is used to represent the size of the real number. In both in oaths of representation, in oaths of standard, the first bit is always used to represent the size of the real number. And if S equal to 1, this is the negative number, and if S equal to 0, this is positive. Okay, and the next bit is used to represent the exponent. Because we use a floating point, so we need 3 value. The exponent, right? The matrixa. And here, because we know already the radix equal to 2 equals a fixed, the radix equal to 2, so we need only two information, that is exponent and matrix. So for the single precision, we need 8 bits from bit number 30 to bit number 23 to represent exponent, and we have 23 bits from 0 until 22 to represent the matrix. And for the double precision, the bit number 64 for sine, bit from 52 until 62 for the exponent, and the bit from 0 until 51 for matrix. And the last one for the extended double precision, the first bit 79 for sine. Here 15 bits from 64 until 78 for exponent, and 64 bits from 0 until 63 for matrix. So we know that here E for exponent and M for matrix, but I write here small e and small m, right? But in this formula I write big M and big E, so it is different. This is different. So big M is matrix, big E is exponent, but in this standardization, small e and small m. So from E and M, how can we find big E and big M? So we use this algorithm. Okay, so for the first bit, S equals 0, positive, 1, negative. Okay, so for the exponent, so E is small e is excess of big E. So from small e, you can find big E. So from excess, you can find exponent using this formula. So exponent big E equal to small e minus B, in which B equal to 127 if we use single precision, B equal to 1023 if we use double precision, and B equal to 16,383 if we use extended double precision. And here we have the formula to find exponent E for different standard, right? So M is the fraction part of big M. So from M we can find the matrix big M. So big M equal to 1 point small m, because small m is a fraction part and the integer part is 1. Okay, so from this representation, we know the side bit S, we know the excess of exponent small e, we know the fraction part small m, we can find the big E and big M. And if we know big E and big M, it means we can find the values of the number by using this formula with the radix I equal to 2, right? So this is the way to represent the number in using IEEE format. Okay, so an example. Here is the formula. So given the representation, you can determine the values of x using this formula. So x equal to minus 1 power s. So if s equal to 1, so it equal to minus 1 and is negative. So if s equal to 0, so minus 1 power 0 equal to 1. It means it is positive. Okay, so we have a matrix 1 dot m, and we have a exponent r equal to 2 power small e minus b, in which b can be found here, right? Example here. So given x, which is represented using IEEE format with 32 bits. So this is single precision, right? So how to determine the value of x? First of the first bit is 1. So this is negative, right? And then we find each bit that is used to represent the exponent. So we have exponent e equal to 1, 0, 0, 0 here, and 0, 0, 1, 0. That is 8 bits that is used to represent the small e. And the rest bit is used to represent the fraction part of the mantissa. Okay. So you can find, okay, example, small e equal to 1, 0, 0, 0, 0, 0, 1, 0. It means equal to this is 128, and this is 2. It means small e equal to 130, right? So you can find that big E equal to small e minus 127. So big E equal to 3. Okay, so we know that the sign bit equal to 1. It is negative, and the exponent equal to 3. And about this mantissa, okay, 1, 2, 3, 4, 5, 6, 7, 8. Okay, mantissa equal to 0.101011. And okay, so I write here. For the first one, we can okay, we can have x equal to 1 dot. Okay, sorry, 1, 2, 3. Okay, 0, 1. Sorry, 1, 0, 1, 0, 1, 1. Okay, 1. Okay, okay. So this is the real number of the first example, and also you can find the results of the second example here. Okay. So in this example, the exponent e equal to 3, radic equal to 2, and the mantissa equal to 1.101011. Okay. The second example is the same. And in the third example, given a real number x equal to 6.375. So how can represent x using IEEE format? So in the example 1 and 2, we give the representation and we find the value. But in the example 3, we given the value and we find the representation. And how can we find the representation? Okay, so the algorithm as following. First of all, we convert this number into decimal system into the binary system, right? We convert this in the decimal system into the number in the binary system. So what is the result? Can someone convert this number from decimal system into the binary system? Can someone give the answer? Okay, so x equal to 6.375. Okay, this is a real number in the decimal system. First of all, we need to convert it into the binary system. So we convert the integer part, right? So 6 equal to 110, right? So this equal to 011. Okay, right? So x, right? and then we write as following: x equal to 1.10011, right? Multiple with 2 power 2, right? Is it correct? Right. So now we have enough information to find representation. Okay, it means we have r equal to 2 because we use binary system. We have a s equal to 0 because it is positive. So we have e equal to 2, right? So we have small m equal to, okay, we have big M equal to sorry, okay, we have big M here. So small m equal to this one, right? So small e equal to 100 n equal to 100 n, right? So now you can find the represent. So small e, because we use 8-bit to represent small e, so 129 is equal to 1, 2, 3, 4, 7, 8, 9. Okay, sorry. So here, okay, this is small e, right? So the representation of 6 dot sorry, representation of 6 dot 375 equal to, okay, 0 for psi, and this one for p, and also this one for m, and okay. So can you see here is a way to find the representation of number x equal to 6.375. Okay. So now you know the way to find the representation of a real number using IEEE format. First we convert number from the decimal system into the binary system, and then we write using floating point number, and from that you can find the information of exponent and mantissa here. Okay. Okay, so do you understand, Cao Sơn?
Yep.
Okay, good. And how about the guy Trương Tuấn Huy? Do you understand?
Yes.
Okay. The guy Osama, you understand? Osama? Okay, I don't know where I even. Okay, so this is the way to represent a real number in the computer. There are some notification. So if all bits of e, small e, are 0, and all bits of m are also 0, so then x equal to 0. If bit s equal to 1, so it's minus 0, and if s equal to 0, it is plus 0. So we know that minus 0 and plus 0 are different. It's not correct. Example, I have this number 0.0000. We have many 0, right? And then 1. So this is 0 in computer, but this is positive 0. Because example, if we use a single precision, so we can only represent 8 number of fraction part. Sorry, six number of fraction part. So if the number is smaller than 1 per million, so it means it is represented as 0 in the computer, but actually it's different from 0, right? So the plus and minus 0 are so different. Okay, the second one, if all bits of E are 1 and all bits of M are 0, so it again is infinity number, right? Infinity number. And finally, if all bits of E are 1 and at least one bit of M is 1, so X is not a number. Okay. You have some range of representation with different kinds of format, single, double, or extended double precision. So each one has different range of representation. Of course, if it is only 32 bits, so the range is small. And if you want to calculate or computing or computing more details and with more exact, right? We need a bigger number of bits, example, double or extended double precision. Okay. Okay, it's the same. So this formula is correct. So x1 divided by x2, so equal to m1 divided by m2 multiplied with r over e1 minus e2. So this is correct formula, right? The last one, how to represent characters in computer. So what is character? Character example A, B, C until Z. So we have a small k and uppercase. Total we have a 26 characters in English, right? So small k and uppercase is 52, and then we have a 10 digits from 0 until 9. Okay, so we have a lot of sign, we have a lot of control character. So that as character. Then how to represent this character? So we need a standard given by ASCII. So ASCII is an American National Standard Institute. They propose a standard, namely ASCII. Okay, so ASCII uses 8 bits to represent character. So 8 bits, it means we can represent 2 power 8, that equal to 256 character. And because the number of character is small, 256, so we can only represent the English character or Latin character. So hence we cannot represent other language like Vietnamese or Chinese or Japanese or Russian, right? Because there are different character, different sign, different language, and hence nowadays most of computer use Unicode format. So Unicode format use 16 bits, and hence we can represent 2 power 16 character. So with this number of character, you can represent most of language in the world. Okay. So example here, this is ASCII format. So example to represent the character big C. Okay, big C here. So it means big C, the number of round is 4, and the number of column is 3. So to represent big C, we use the hexadecimal number 43. It means when we type the key C in keyboard, so we will generate a series of binary digit 4 3. It means 4, it means 0 1 1, sorry, 1 0 0, right? And 3 is 0 1 1. So it means when we type in the keyboard the sorry, so when we type in the keyboard the character big C, it means the keyboard will generate a series of a bit that equal to 4 3 in the hexadecimal system, and it will generate a binary number 0 1 0 0, that is 4, and then 0 0 1 1, right? So when you type the character big C in the keyboard, so keyboard will generate this series bit, right, and send to the CPU, and then CPU will understand this kinds of number, and then they display on screen the number, the character C, big C. Okay, so this is the way to represent characters in computer. Okay, so do you understand? Okay, so time's up. So today we stop here, and I will have information on the teams for the next week. Okay, so bye bye.